$180 billion US. A high-speed rail network cutting straight through the Southwest's most active geothermal belt, where underground magma pockets constantly push rock temperatures up to 450 degrees Celsius. This is no ordinary transportation project. It is a direct confrontation between modern metallurgy and Earth's shifting tectonic pressures. As the bullet train roars through the subterranean world at 350 kilometers per hour, the aerodynamic pressure generated within the narrow tunnels is absolutely immense. But that is not even the greatest challenge. The real defiance lies in a geological depth exceeding 2,500 meters. At this extreme depth, rock wall stress can easily crush conventional steel structures. For standard tunnel projects, engineers rely on typical TBMs with carbon alloy shields. But at this thermal coordinate, heavy-duty hydraulic seals would melt after 15 minutes. Hydraulic fluid completely loses viscosity at temperatures above 120 degrees Celsius. The drill cutters would seize up due to uneven thermal expansion of metal. If the tunnel shell deforms by 2 millimeters, the digital guidance system loses precision. To bypass the volcano's unstable core, the railway must extend toward the high-pressure coastal shelf. Here, engineers confront deep-sea construction under constant threat of submarine tectonic shifts. Enormous offshore drilling platforms are anchored directly into violent waves of the open sea. Industrial operators endure relentless maritime storms, working tirelessly under freezing ocean spray. They secure massive steel foundation piles plunging thousands of meters into the ocean floor. Back on rugged land slopes, a heavy automated laser blasting fleet begins fracturing volcanic basalt. Blinding plasma energy bursts strip away layers of igneous rock with mechanical precision. A synchronized conveyor system then carries hot, crushed minerals out of the mountain core. Heavy-duty robotic arms line the exposed path with advanced multi-layered polymer support rings. High-powered jet fans are installed to blast away toxic sulfur gases escaping rock veins. The custom high-temperature TBM shield machine officially locks its cutting head into position. Dozens of spinning cobalt tungsten teeth grind into thermal granite, generating intense sparks. An automated high-pressure system constantly floods the cutting face with synthetic coolant fluids. Industrial teams monitor the structural integrity of giant hydraulic pistons from secure enclosures. Every movement is calculated to ensure the structural shell withstands Earth's internal pressure. To counter extreme heat radiating from the core, unprecedented cooling infrastructure must be constructed. Engineers deploy high-pressure pipelines to circulate liquefied nitrogen directly into active rock strata. On the coastal perimeter, workers battle maritime surges to erect a wave breaker wall. Relentless ocean waves slam against reinforced steel caissons as crews anchor the foundations. Despite brutal marine storms and freezing spray, the team successfully secures underwater concrete monoliths. Deep inside the main gallery, an advanced rig injects liquid silicate polymers into fissures. Blinding green laser scanners sweep the rock face, mapping microfractures onto engineering grids. A specialized fleet of robotic arms begins placing high-strength carbon fiber reinforced mesh along ceilings. Giant shotcrete machines blast advanced heat-resistant concrete layers to seal volcanic rock permanently. Simultaneously, massive automated explosive charges are precisely laid by robotic units into shafts. The subsequent controlled detonation utilizes advanced plasma waves to disintegrate hard granite formations cleanly. A powerful magnetic conveyor system immediately extracts highly metallic rock debris from blasts. Behind the excavation front, automated structural erectors lift steel arches to reinforce the vault. Every dynamic stress level is continuously monitored by fiber optic sensor arrays embedded in walls. This tightly synchronized industrial ballet transforms an active volcanic hazard into a controlled corridor. Once the rock face is stabilized, high-speed rail foundation construction begins under the ocean. Engineers deploy automated subsea casting rigs to pour ultra-dense waterproof concrete into trenches. Out on the open ocean, floating concrete mixing plants encounter fierce maritime storms. Industrial crews in matching neon green jackets work with absolute intensity on heaving decks. They combat freezing saltwater spray and violent ship movements to keep supply lines operational. Back inside the mountain passage, heavy automated track-laying machines advance onto cured concrete bases. Dazzling white electric arcs erupt as specialized robotic welders join titanium-infused steel rails together. A continuous magnetic inspection gantry follows behind, scanning every millimeter for weld micro-defects. Simultaneously, heavy-duty mechanical overhead arms install futuristic copper alloy power catenary grids along roofs. To shield vital electrical systems from acidic vapors, automated nozzles spray anti-corrosive polymer glaze. Next in sequence, structural assembly teams prepare to mount heavy anti-seismic dampening base plates. Giant hydraulic positioners align massive lead rubber bearings designed to absorb extreme tectonic shifting. Bright yellow robotic cranes lift these multi-ton components into place with spatial precision. Every single installation milestone is verified by automated laser tracking nodes linked centrally. This relentless step-by-step mechanical progression secures the world's most dangerous railway line. Following foundation reinforcement, the automated sequence shifts to installing advanced digital signaling systems. Heavy-duty overhead track rigs deploy automated arms to mount communication transponders onto vaults. Simultaneously, out at sea, the Maritime Division faces escalating storms threatening ventilation towers. Industrial operators wearing bright neon green safety jackets fight fierce winds to secure anchors. They endure freezing ocean water spray, working relentlessly to prevent ocean breaches into intakes. Back inside the subterranean corridor, a geological stabilization machine injects liquefied nitrogen into fissures. Blinding cyan laser tracking arrays sweep volcanic layers, computing stress variations onto digital screens. A synchronized fleet of rock bolting vehicles drills deep into basalt, securing walls with carbon fiber. Giant automated robotic arms then line perimeters with thick, multi-layered thermal insulation panels. To break through a dense granite plug ahead, automated units precisely plant plasma charges. The subsequent controlled electronic detonation uses energy shockwaves to cleanly pulverize the rock face. An automated heavy-duty vacuum system immediately sucks thousands of tons of dust away. Behind this blasting front, massive mechanical lifters lock reinforced steel lining segments into arches. Every single dynamic movement and vibration level is continuously cross-checked by embedded sensors. This massive industrial chain ensures the volcanic cavern is transformed into a safe artery. Following vault reinforcement, the industrial pipeline transitions to deploying heavy subsurface drainage systems. Automated trenching vehicles cut deep channels, laying high-strength titanium drainage pipes to divert water. Out on the open ocean, maritime construction crews face monumental storm waves pounding docks. Industrial operators in neon green jackets brace against fierce winds to secure supply pipelines. They endure freezing ocean spray and vessel swaying, preventing seawater from flooding lower shafts. Deep back inside the passage, advanced pressure grouting machines inject rapid hardening liquid granite composite. Blinding green laser alignment arrays sweep the vault, mapping rock consolidation density instantly. A synchronized fleet of rock anchoring rigs drills into high-temperature basalt, sealing strata with rods. Giant automated overhead mechanical lifters line ceilings with multi-layered thermal shield panels. To obliterate a dense pocket of volcanic ore, automated arrays install plasma charges. The subsequent controlled electronic blast releases focused energy shockwaves to pulverize the rock face. A high-powered, automated conveyor matrix immediately carries thousands of tons of debris away. Behind this blasting front, massive hydraulic structural erectors lock steel lining segments into arches. Every single thermodynamic stress level is continuously monitored by embedded fiber optic grid sensors. This massive operation ensures that the high-pressure volcanic chamber is fully secured into corridors. With structural drainage and insulation layers finalized, workflow progresses to installing heavy rail tie-downs. Automated torque vehicles deploy dual robotic arms to clamp alloy anchor bolts into floors. Simultaneously, out on the dark ocean, the maritime infrastructure experiences a massive tempest. Industrial operators in neon green jackets hold fast against roaring winds to guide rings. They withstand freezing ocean foam and hull pitching, preventing waves from flooding intake shafts. Deep back inside the corridor, an advanced geological injection unit pumps ultra-dense silicate compound. Blinding cyan laser telemetry arrays sweep cavern walls, mapping microscopic tectonic shifting onto grids. A synchronized fleet of rock-pinning rigs drills into active strata, locking the mass. Giant automated overhead mechanical hoist modules line vaults with thick ceramic thermal shielding tiles. To completely shatter a massive wall obstructing the path, automated crawlers insert plasma charges. The subsequent electronic shockwave detonation utilizes advanced energy fields to atomize solid rock faces. A high-powered automated suction matrix instantly extracts thousands of tons of smoke and debris. Behind this excavation line, massive hydraulic segment erectors lock steel lining modules into arches. Every single dynamic stress level is continuously evaluated by embedded fiber optic telemetry sensors. This massive continuous industrial chain successfully tames high-pressure volcanic geology into pristine rail corridors. Following rail anchoring, the automated sequence transitions directly to deploying subsurface communication relays. Automated trenching units deploy dual mechanical cutters to slice deep floor conduits for lines. Simultaneously, out on the treacherous ocean, marine engineering teams encounter a fierce tempest. Industrial operators in neon green safety jackets fight severe wind forces to anchor breakwaters. They endure freezing ocean spray and structural shaking, preventing sea breaches into lower shafts. Back deep inside the passage, heavy automated pressure grouting machines force composite into active fissures. Blinding green laser alignment arrays sweep the cavern vault, mapping structural integrity changes in real time. A synchronized fleet of rock bolting crawlers drills deep into high-temperature basalt, securing rock with rods. Giant automated overhead mechanical lifters line perimeter ceilings with heavy ceramic thermal panels. To obliterate a dense pocket of granite ore, automated drilling arrays install plasma charges. The subsequent controlled electronic detonation utilizes advanced energy shockwaves to cleanly pulverize the face. A high-powered automated conveyor matrix immediately carries thousands of tons of debris away. Behind this blasting front, massive hydraulic structural erectors lock steel lining segments into arches. Every single dynamic stress level is continuously cross-checked by embedded fiber optic grid sensors. This massive industrial pipeline successfully secures volcanic geology, turning extreme hazards into controlled routes. With all core structural segments permanently locked, the mega pipeline transitions to deploying power switching modules. Automated rail gantries deploy motorized robotic arms to assemble digital substations within safety bays. Simultaneously, out across the violent marine grid, the offshore task force battles an intense typhoon. Industrial operators wearing neon green jackets stand firm against howling winds to secure sea anchors. They endure brutal ocean spray and relentless hull slamming, maintaining stabilization for undersea links. Back deep inside the passage, heavy-duty chemical injection systems seal hidden fault zones with polymers. Blinding cyan laser telemetry arrays move along concrete walls, transmitting precise stress data directly. A synchronized fleet of rock anchoring rigs drills into volcanic rock, pinning layers with rods. Giant automated overhead mechanical hoist modules line perimeter vaults with ceramic thermal shielding panels. To obliterate the final massive wall blocking the line, automated units precisely plant charges. The subsequent controlled electronic detonation uses advanced energy shockwaves to completely vaporize the face. A high-powered automated conveyor matrix immediately carries thousands of tons of debris rapidly away. Behind this blasting front, massive hydraulic structural erectors lock steel lining modules into arches. Every single thermodynamic stress level is continuously cross-checked by embedded fiber optic grid sensors. This relentless, step-by-step mechanical progression secures the final layers of the dangerous railway. With the entire engineering pipeline completed, the final tracks are systematically energized for checks. Automated catenary test vehicles roll forward, mapping electric current flow across the dark corridor. Out on the harsh coastline, maritime crews secure final subsea intake locks against waves. An ultra-modern streamlined bullet train pulls smoothly into a brilliant, multicolored terminal station. This documentary is for education only, based on real sources. Theories are not facts.